Welcome to the Science Seminar brought to you by the Southeast Climate Adaptation Science Center, also known as Southeast CASC or CCASC, the others referred to as both. My name is Michelle Jewell, and I'm the new Communications and Engagement Manager here at the Southeast CASC. And I'm joined today by Kristen Fontana, Science Communication Fellow here with us. And in these virtual seminars, we are highlighting CCASC work supporting research management across the Southeast. So let's start with letting you know what to expect from today's webinar. We'll go over some meeting logistics, request some feedback via a short poll, then introduce our speaker for today. They will present for 40 to 45 minutes or so, and then we'll have some time for Q&A at the end with a discussion. And now I'll turn it over to my co-host, Kristen, who'll give you a quick overview of our webinar tech. Kristen, take it away.
So I'm going to quickly cover some of the features of the Zoom interface that we're using for today's webinar. I'm sure that we're all pretty familiar with Zoom at this point, but we do recognize that folks do use different technologies, so I'm just going to point out a few things. The controls on the bottom left of your Zoom screen allow you to mute and unmute your audio. We will keep all lines muted and ask that you also keep your video off so that we can reduce distractions during the presentations. In the middle of the bottom bar, you can access the chat window. And I'd encourage you, if questions come up during the presentation, to submit them in the chat for discussion after the talk. We'll be monitoring questions there and we'll pose them to our speaker during the Q&A session. We will also be recording today's seminar, and you can access and share the recording afterwards on the Southeast CASC website, on our Science Seminars webpage, and also on our YouTube channel. Now we're going to launch a short poll just to get a little bit of information about who is with us today and to help us know how to continue to get information about these seminars. And we'll give you just about a half a minute or so to fill it out. Okay, and then whenever Carrie is ready, she'll share the results for you guys. Thank you guys for filling this out and for feeding back this information. It's great to see the breadth of folks in our audience today, which sets us up for a robust discussion about this research. Now we'll turn it over to our presentation. And while we switch screen sharing, I'll introduce our speaker. So Hemant was a 2020 to 2021 Global Change Fellow. He is a PhD candidate in the Department of Civil Construction and Environmental Engineering at NC State University, and he develops tools to study the interconnectedness of food, energy, and water systems, also known as the Food, Energy, Water Nexus. The title of his presentation is Using Deficit Irrigation to Reduce Vulnerability in the Food, Energy, Water Nexus. Now I'll turn it over to you, Hemant.
Good morning, everyone. My name is Hemant, and today I'll be discussing about my work on using deficit irrigation to reduce the vulnerability in the food, energy, water nexus. This work is part of my PhD dissertation. I partially did it when I was a Global Change Fellow at CCASC. This work was recently published in the journal Water Resources Research. So starting up, food, energy, water security. Now, food, energy, water security refers to availability of food, energy, and water resources for everyone, and it is critical for sustained growth of human civilization. However, recent anthropogenic impact on the planet have called into the question whether our planet can support the continued human growth. There have been some progress. For example, the United Nations launched Sustainable Development Goals, like which have zero hunger and water availability for everyone as one of the goals. However, despite some progress in this area, there are still some challenges associated, which are mainly related to the interdependency of the food, energy, water systems on each other. So I will explain how these systems depend on each other, and then how can we go about solving it. So beginning with the food, energy, water nexus. So it all centers around consumers, whether they are located in cities or industries or in the countryside. They are at the center of all of these systems being food system, energy system, and water system, where each system supplies different things to the consumers. For example, water system supplies domestic water supply, food system supplies grains for consumption. And then these systems also get return flows from the consumers. For example, treated wastewater to water sector and food waste to food sector. Now, these systems are not working in isolation. They are also interacting with each other. For example, water is needed to irrigate crops and generate grains. And then we use energy to treat and distribute drinking water. And furthermore, these are not one-way flows between these sectors. We have multiple directions. So for example, growing crop, it impacts the water quality of the region as well as water availability. We also use water to generate hydroelectricity and in turn use energy to irrigate fields for growing food. Now, this is a complex system and humans are also involved. So how do we analyze it? So the central spokes, that is the orange and blue arrows, they are what we term as system delivery metrics. Their goal is to supply the utilities to the consumers at the lowest possible price in a reliable and safe manner. These have been studied a lot in the past and optimized a lot. For example, how much does it cost per kilowatt hour of electricity? Government agencies and public utilities have tried to minimize it over time. And we have a good understanding of these links. However, the links between the different sectors, they have not yet been studied that thoroughly. And only recently we have begun to study them. For example, consider the water to food, the purple arrow. How much of increment in yield we get? That is, how many more bushels we can grow per acre for each acre feet of water supplied. So that is one such link. Another is, if we are using water to generate hydroelectricity, that is water to energy, the green arrow, how much hydroelectricity revenue is generated for the stream flow diverted for this purpose. So these green and purple arrows are what we term as food energy water nexus. And this work is in this context. Now, this nexus is also impacted by climatic variability at every stage. So if we have a drought, our food production is hampered. We do not have water available. So we cannot generate hydroelectricity and we cannot irrigate crops. So there are multiple links which are impacted by climate. In today's work, I'll be focusing specifically on the water to food link, which is highlighted here in the pink color, the purple arrow. If you have, we are irrigating to generate food, how do we incorporate the interannual climatic variability? That is, sometimes we have more than normal rainfall, sometimes we have less than normal rainfall. So how does it impact the food production? Now, to study this, I am considering a river basin named Flint River Basin in the southeastern United States. As you can see on your screen, it is located in southwest Georgia. Now, Flint River Basin is a basin where agriculture dominates the economic sector. It contributes about $6 billion annually in direct and indirect economic benefits to the basin's economy. And furthermore, most of the agriculture depends on supplemental irrigation. What may mean supplemental? If you take, for example, arid regions of California, you have agriculture is happening with all the water requirement being met by irrigation. However, in the southeast, we do have plenty of rain, But in the growing season, sometimes the rain is less than normal. So that is where we supplement the crop's water requirement with additional irrigation. That is called supplemental irrigation. So, and agricultural irrigation is a major water use. It comprises around 90% of the total water needs of the region during the growing season. And 70% of the irrigation, that is around 400,000 acres, relies on groundwater from the Floridian aquifer. Now, withdrawing a lot of groundwater from the ground, it impacts the groundwater table as well as the available flow in the nearby streams. And the situation has worsened to the point that in the last 20 years, 2 times the Georgia Environmental Protection Division had to suspend issuing new groundwater well permits, and because the water was not available for the municipal uses, and pay farmers to not to irrigate during these long droughts. So our objectives in conducting this work are, can we model year to year crop yield variations? So sometimes you have 35 bushels per acre, sometimes you have 40, and it is a large variation. So how do we model it? Then the second is, can we link the crop growth simulation model to the profit maximization model for the entire basin? Then we have, can we find optimal crop and irrigation portfolios? That is, which crops to grow and how to irrigate them to maximize regional profits while minimizing water use. Fourth, there is this technique called deficit irrigation, which I will introduce. We explore how this technique can be used to improve yield with reduced water availability and reduced energy availability. And furthermore, finally, how does this strategy vary across above normal and below normal years? So I will introduce this technique before going into the model details, deficit irrigation. So consider this case. We have different years on the x-axis, and we have the yield, crop yield per unit area on the y-axis. So if we just have all the crops water needs are met with rainfall, we call this rain-fed agriculture, and we can expect some certain amount of yield. However, if we were to meet all of the crops requirement, water requirement, that is, we are irrigating almost daily, and however the crop needs, we are providing it, that is what we term as full irrigation. Now, there are also cases where we do not supply full irrigation amount, we supply partially, we are partially meeting the crop's water needs. So that is called as deficit irrigation, deficit being that less than full. Now, this deficit irrigation can be provided in multiple ways. We can schedule irrigation differently. We can increase the interval between irrigation events. So we have two parameters called alpha and I. Alpha refers to when do we irrigate. If the soil moisture goes below a certain threshold, then we irrigate. And I refers to the how much water are we supplying per day, so the maximum rate of irrigation. So alpha is the frequency and I is the intensity. Now, this technique has been studied in the past in literature and has been found to save water while increasing yield. We have incorporated this in our model. Now, coming to our model, we have this threefold approach. I will not go into the exact details of the model. I will give a brief overview. So the model has three parts. First is the crop growth model, which we use AquaCrop OS, which is an open source model, which takes in weather inputs, the soil characteristics, crop characteristics, groundwater availability, everything, and then it gives us how much yield at the end of the season we can expect. Then second is what I had shown before. So you have yield under rain-fed conditions and under full irrigation conditions. Now we can generate scenarios where we partially meet the crop's needs. And then using that, we can develop a model which calculates how much yield we can expect when we supply some unit of water. So this model will give rain-fed yield if we do not supply any water, and if we supply all the crop water needs, then it will give the full irrigation needs. And it can also give the yields in between depending on the value of alpha and I. Now the third component is we have the crop prices, production costs, land availability, and groundwater pumping costs. And considering them, the model outputs how much of each crop to be grown under rain-fed conditions, under full irrigation conditions, and deficit irrigation. And as well as how much, what is the frequency and intensity of the irrigation in the deficit irrigation scenario. Now, presenting some of the results. First, I'll be presenting this crop growth model results. So we calibrated our model for 4 crops, that is corn, cotton, sorghum, and soybeans. Combined, these crops account for 65% of the cultivated acreage in this region. Our model spans 21 counties, and then we have the study period of 1980 to 2010, and the validation was performed using leave and out cross validation. So this is a sample time series where you on x-axis you have the years 1980 to 2010. On y-axis you have the yield per unit area. This is for corn grown in Worth County, Georgia. You can see the blue is the yield surveyed by US Department of Agriculture, named NAS yield, and the orange line is what our model is estimating. And you can see that the large interannual variations the model is able to capture well. Now, I will not go full results of this. I will go to the results of the third section, which is how much of each crop to grow and each crop to irrigate, and then how to maximize regional profits. So it's important to understand what the model outputs. So as I stated earlier, we have 4 crops: corn, cotton, sorghum, and soybeans. And then for each crop, we have the rain-fed acreage, we have the irrigated acreage, we have the deficit irrigation acreage, and then how should we do the deficit irrigation? That is the optimal alpha, that is frequency of the irrigation, and I, that is the intensity of irrigation. So in total, the model gives 20 outputs for each county in each year. Now, how do we validate this model? So what we did, we have the how much of each crop is grown and how much each crop is irrigated or not irrigated from the US Department of Agricultural data at county level. So we have the yields also from there. We also have the yields from our calibrated model, AquaCrop OS. So we look at both of them. So here you can see in terms of revenue and profit, we calibrated the model yields to not overestimate. So if we are getting 30 bushels per acre, we calibrated the model conservatively so that it does not overestimate the yield. So we do not get fictitious benefits when we are doing the analysis. So here you can see the pumping cost and the other cost will be same for both of them. However, the revenue and profits will be different because the yield values estimated are different. The colors are corresponding to different crops. We are interested in the total values. Now, we can also look at how much energy has been used for pumping, how much water has been used for pumping, how much of acreage, total acreage was used, how much acreage was under rainfed irrigation and under irrigated irrigation. And you can see in both of these, no acreage is under deficit irrigation. So the area will be same, only the yield values are different. And we know the difference. So now going forward, AQ1, that is the yields we are using from our model, that will be our baseline. Yeah, I already covered it. So the baseline will be AQ1. Now we want to investigate what happens if we introduce deficit irrigation while maintaining crop diversity. So that will be the scenario AQ2. So I will cover it briefly. So first of all, we have the baseline AQ1 revenue, and we can see if we allow deficit irrigation and allow the model to optimize it, we can see that the total revenue is increasing by 18%. Further, the profits are increasing by 51%. All of the profits and everything is presented in $2010 adjusted for inflation. Then we see that the amount of water pumped has also decreased compared to the baseline scenario, and the energy used has also decreased by 40%. Now, I mentioned crop diversity. So this is crop diversity is that we do not change the observed crop portfolio drastically. We are keeping existing diversity, and then we are investigating, does there exist a more optimal portfolio which can increase the regional profits and revenues and reduce the water used for irrigation. And we can see that the AQ2, by allocating a lot of irrigated acreage to deficit irrigation, it improves the revenue and it improves the profits. Now, here we are maintaining crop diversity, but what if we do not have that constraint? So we can just choose the most economical crop and strategy. So that is what we term as AQ2M, and I will show here. So the revenue goes up 42% compared to 18% earlier. The profits nearly double, more than double. And then the water applied, we have a reduction in that because more groundwater pump is used to increase the yield and thus increase the revenue and profit. But as a result, we do not get that much water saving as we got in the previous scenario. And similarly, energy used is also reduced. So we can see that we do have a range of portfolios which are available than the existing ones, which can have higher revenue and profits for the region with reduced water application. So next we investigated how do we irrigate in dry years, that is years when we do not have enough rainfall or less than normal rainfall. So on the x-axis, the years are arranged. We have 31 years and they are arranged from having the lowest seasonal rainfall to the highest seasonal rainfall. So the years on the left are some of the driest years, and on the right, they are some of the wettest year. And then on the y-axis, we are showing how much of the total acreage is under rain-fed irrigation, that is the blue line, the deficit irrigation, the green line, and the full irrigation, that is the orange line. So what you can see is that deficit irrigation is the preferred strategy in very dry years, where almost more than 40% of the acreage, even more than 60% of the acreage is under deficit irrigation in driest years. Next, in wet years, intuitively we know it does not make sense to irrigate, and that is what the model is outputting. So in wettest years, rain-fed is the preferred strategy. In normal years, we have there is no clear preference between deficit and rain-fed irrigation, but it depends on the crop, the prices, the local conditions. Now, we investigate why this is happening, why deficit irrigation is more beneficial than full irrigation or even rain-fed irrigation. So here I am showing for a single county 3 years. Year 1993 was below average seasonal rainfall. Year 1981 was average seasonal rainfall, and 1984 is above seasonal rainfall. On the x-axis, we have the frequency of irrigation, and y-axis we have intensity of irrigation. Yellow color means we are getting higher yield per unit area. Green color means we are getting less yield per unit area. Now, if you look at the lower right picture, all of these 3 years are shown. So you can see when we have above average rainfall, irrigation nominally increases the yield. That is, without irrigation, we are getting around 52 bushels per acre. And with irrigation, we are getting 58 bushels per irrigation. So not that drastic increase. Now, if we consider an average rainfall situation, irrigation increases the yield from 44 to almost 55. And if we consider dry years, so supplying irrigation water, it increases the yield a lot. So it starts from around 28 bushels per acre, and it goes all the way up to 55 bushels per acre. So it is more meaningful to irrigate in dry years when the crop's water needs are not met. Now, we understand that it is more impactful to irrigate in dry years, but how does that impact the cost? So here I am showing the same figure, the previous figure in a different way. So on the y-axis, we still have the crop yield in bushels per acre. On the x-axis, I have combined how much water is supplied for irrigation, that is millimeters per acre. Earlier we had alpha and I, now we combine all of these cases. So each dot here represents to one. Here you have squares, and here that square turns into a circle. So now we see same observation in when we have average rainfall, that is the orange points, we see that the irrigation increases the yield and thus increases the revenue, but it also requires a lot more water. That is the water applied for irrigation on the x-axis. Now, when we have above average rainfall, the yield increases and revenue increases little bit, but the cost, they increases proportionally more. And finally, when we have below average rainfall, we can see that the yield increases drastically while the water applied increases slowly, that is the costs increases slowly. And we can name, this behavior is known as diminishing gains in crop yield with additional supplied water. So in dry years, supplying the initial few units of water, it increases the yield, but after a point, the increase in pumping cost does not translate into a proportional increase in revenue. Now, we also looked at what would be the depth when it will become uneconomical to irrigate. So we, on the x-axis here, I'm not discussing all the figures. On the x-axis, we have how much the groundwater deepens. Fortunately, now currently in the Flint River Basin, the water depth is not that deep. But if it becomes deep, then we can see that the rain-fed irrigation is preferred over deficit irrigation after some time, because it just becomes uneconomical to irrigate. The pumping costs are too high, while the increase in yield is not that much proportionally. Second, we also investigated if energy availability is challenged, whether it is through the impact on gas prices or impact of electricity prices. So we see that on the x-axis, we have the increase in energy costs, and on the y-axis, we have the frequency of irrigation. We can see as the energy becomes less available, the crops are irrigated less frequently in deficit irrigation. As well as we see that in dry years and wet normal years, the deficit irrigation acreage slowly gives way to the rain-fed irrigation, that is the purple line. And the impact is more in dry years, that is the above 2 rows, than in normal years. So finally, coming to some conclusions, the model is able to estimate the year-to-year variability in crop yields. Then we have the model is able to facilitate mixed irrigation, that is rain-fed, fully irrigated, and deficit irrigation strategies. We observed that the rain-fed and deficit irrigation strategies are preferred over full irrigation. And we noted that especially in dry years, it makes sense to irrigate. And after that, after the initial amount of irrigation, we have diminishing gains in crop yield with additional supplied water. And it happens because the pumping cost increases while the revenue does not increase that much. We also looked at if the groundwater table deepens too much, then it becomes uneconomical to irrigate. Yeah, so this is the study, and I would like to acknowledge the support from the CCASC and NSF, as well as my collaborators, Dr. Arumugam and Dr. Chu. Yeah, I finished it early. Now we can have plenty of question answers. Yeah.
Wonderful. Thank you so much for the lovely talk. Folks, as you have questions, feel free to throw them in the chat. We'll give you a few moments to do that, or you can raise your hand if you have a question that you'd like to be brave and ask out loud. I have a question to kick us off, acknowledging first my complete ignorance of this field. So I apologize if this question is completely off base, but I was curious, we're speaking about rainfall. Would this model, or what types of variables might you have to consider for this model for things like floods or like extremes of water on the ground that maybe don't necessarily have to do with immediate rainfall? I'm thinking like coastal type, or take it whichever way you like.
So for now, this model is not near the coast, but still we can have flash floodings even in inland. So we haven't, this model still is not able to incorporate them. So those damages are relatively less. In agriculture, what is more prominent is we usually have long-term water scarcity, and that impacts the yield. So especially if those impacts that you are talking about, they are, let me put it this way, you have different stages of crop growth. So you have when the seed is just sprouting and then the seed is maturing. So at early stages, those impacts like flash flooding can reduce the crop yield, but afterwards the crop is more resilient to it. But still there can be hails or other events. We are just focusing ourselves on if you have reduced water availability, how does that impact?
The typical question of, hey, that's a great model. How about something completely unrelated to it? So I apologize for throwing that at you. Wonderful. Any other questions? Any folks in the, Carrie has in the chat here, somewhat related, is it possible to incorporate extreme events or variability within year rather than annual averages?
Yeah, so it's a great question, Carrie. So the model which runs on daily scale, so we in the growing season, we typically have 100, 120 days. So each day's rainfall, temperature, humidity, wind speeds, we consider all that. And then the model runs at daily level, and then finally it gives us a seasonal yield value. So if we have, say, what happens if it did not rain for the entire 2 weeks, the model is able to incorporate that. And we designed it. Yeah, I would like to, like, that's the question, some extension. So the model is aimed for regional water planners. So for, say, the water manager responsible for the entire basin, model can be used with, if we have short-term forecasts available, seasonal forecasts we have, how much above or below normal precipitation, or whether we are about to get some coincidental successive events or a large gap between rainfall events. The model is able to capture that, and then using that, the managers can make recommendations on which crops to grow or how to irrigate or what to prepare. Yeah.
Thanks, Carrie, for the question. Oh, Olivia's gotten here. Have you shared these results with irrigators? What have been their reactions?
So we have not shared it with individual farmers, but we have promoted this work through different channels. US news service, university news services, as well as this has been covered by Associated Press. And through emails and others, we have also reached out to different people. We are waiting, like, if someone is interested in taking it to the next level, then it can become a product. But as far as of now, the reviews we have gotten from, like, other researchers and reviewers, they are very hopeful, and that it fills the need of, you have for each season, if we can make recommendations and you can quantify, okay, if you do this, then this much more profit you can make, or this much water savings you can make. Yeah, but not individual farmers as of now.
Great, thanks.
If there is interest, yeah, we are open to. So right now it's at the county scale, so it's still pretty coarse, but we can further increase the resolution if there is a lot of interest in it.
Wonderful. Any other last dying questions for Hemant?
Can I jump in? Sorry, I'm just going to unmute because it's easier. I can talk faster than I can type, for absolute sure. So, and I think we talked a bit, maybe a little bit about this before you started, Hemant. So is it possible to pair this with stream flow modeling to sort of see the implications of some of this deficit irrigation potentially on, you kind of mentioned streams at the start, for how that might then play out into more ecological flows in the surrounding some of these areas.
Yeah, so so this is in the Flint River Basin, and in the southeast, we do have karst watershed. So that is, you have a lot of interactions happening between the surface water and groundwater. And if you pump water out for irrigation, it impacts a lot on the base flow to the surrounding nearby streams as well as the surface runoff. So there has been some work in the southeast on this. In this one, we have so far limited ourselves to not modeling that impact, but it's an interesting area and it can be extended to that domain as well. So how much of the impact we have, that is, you pump certain amount of water from the ground, how much reduction in the nearby stream you can have as a result of that. So that is the quantity aspect of it. And then we have the fertilizer application and other things which impact the water quality. That is the nutrient load in the stream. So it can also be modeled. So there is some research from University of Illinois Urbana-Champaign where they have focused on this, that impact of irrigation on water quality. But so far it has not been done, but if there is interest, we will be able to extend it.
Great, thanks.
Thanks, Kara. All right, folks. Well, again, thank you so much for the wonderful presentation, for detailing your work today. Much appreciated. I'm going to close out by doing a plug, as we should, for upcoming seminars. I'm going to throw these in the chat as well. October 24th, next week. Oh my gosh, it's the end of October. But October 24th, the Global Change Fellows will be hosting a seminar in the translation of science from research to application and adaptation at 3:30. That link is in the chat if you want to register, or you can click on the QR code there. And then the next science seminar, Climate Change Impacts on Brook Trout Populations in the Southeastern USA, will be presented by CCAS Project PI Yoichiro Kano on November 29th at 11 a.m. Again, link is in the chat there. And I'm betting, oh, yep, we've got the link in the chat there too. Great. Thank you. So those are coming up, and we hope you'll be able to join us for those seminars into the future as well. Also, look out for notices for other upcoming seminars in our newsletter. By signing up for this one, we're going to add you to our newsletter list. And of course, you can unsubscribe from that. But once you see the first newsletter, you will be hooked for the rest of your life with all the events that are coming up. But of course, you're welcome to unsubscribe if you'd like to. Thanks again, everybody, for joining us today. Thanks again, Hemant, for your wonderful presentation. Hope you all have a fantastic rest of your afternoon this Thursday. We'll see you next time. Thank you so much.